let me start today's class. So until the last class, we had talked about lookup algorithms, right? So basically what we were trying to do that, whenever a packet arrives at a router, you basically check that what is the IP address that is in the header, that is stamped in the header of that packet, and then you try to use some efficient lookup algorithm so that you can have a fast lookup with less number of memory access, as well as the storage required for that, for storing the prefixes should be less. So you try to find out an efficient algorithm in all of these aspects, and try to have a fast lookup. So once the lookup is done, then you know that okay, this is the port through which you should be forwarding your packet. Okay, so that is the reason that we were looking for faster and better lookup algorithms. And we also found out that some of the lookup algorithms we saw hierarchical, we saw binary tries, we saw our different disjoint prefix tries, we also saw multi-bit tries yesterday. Okay, so these are some examples that we saw. Now just think about from the perspective of a router. The task of a router is not just simply if a packet arrives, just forward the packet to the corresponding output port. It's just not the task of that is just not the task of a router. A router does many other tasks apart from this task. Okay, now from a user's point of view, a user always has different QoS constraints, right? So the user can have different QoS constraints. There can be different rules that may be applied for packets belonging to different types of applications or different types of users. Okay, so where would these rules be applied? Okay, so whenever a packet is arriving at the router, there has to be some rules that has to be applied to these packets even on those routers when they are passing through, so that the corresponding QoS can be satisfied or supported at the user's end. Okay, so there can be many authentication techniques that should be used for different types of packets depending upon what is the application that packet belongs to. There can be certain different other rules that need to be applied depending upon what is the protocol that is mentioned in that header field of the particular packet. Okay, so there are many other jobs that the router would have to do apart from simply just doing a lookup, finding the corresponding output port, and then forwarding the packet to the corresponding output port. Okay, so today's class we are going to start looking at these extra tasks that the router might have to do. Okay, so that is the topic for today's class, that is IP packet filtering and classification. Okay, so as of now, what we have known is that we have different packets that are arriving at a router. We check the header field for the IP address. We use some efficient lookup algorithms to find the corresponding output port through which the packet should be forwarded. Today we are going to look at that depending upon different QoS constraints or different other requirements of the packet, how do we filter the packet and how do we classify them? And what are different efficient algorithms which can be used for carrying out such tasks? Okay, so this is what we are going to start today. So yeah, let us start. So first is packet classification. So as I was talking about that the service requirement by different packets might be different, right? So a packet can be differentiated in terms of what is the service that it is providing, or what is the service provider's basic rule for that particular service. Okay, or what are the mechanisms that the service provider uses to identify a packet or to isolate a packet from other packets. So these are the methods, few requirements for a packet. Then now if the packet has different ways of being classified, then the forwarding engine has to classify these packets. So how would it do that? It would have to examine the packet fields other than the destination address, because here we are not only considered about the destination address. Right now we are trying to classify the packet, so we will have to look at the other fields rather than simply the destination address, so that we can find out that what is the context of the packet and what are the additional processing tasks or what are the different actions that need to be taken on the particular packet so as to satisfy the requirements of the end user. Okay, now some example actions that we can think of are that you can drop unauthorized packets. So first you need to do an authorization. You need to check that whether the packet is actually an authorized packet or not. If not, then you can drop the packet. Okay, or if a packet is supposed to be highly secure packet, then you may need to encrypt that packet. If there is a packet which is like having a very low TTL, that means it has to be served very fast, very high priority packet. So you have to then, in the queue itself, you have to prioritize that packet for scheduling. That we have already seen earlier also, that many scheduling techniques can be considered for prioritizing, for different ways of prioritizing packets. Okay, so these are some examples of actions that may need to be taken on packets. So those will be specified in the form of packet, in the form of some rules, and with the help of these we need to classify the packets. So this process of differentiating packets is called packet classification. So what is the importance of packet classification? We have already got to know that, different packets may have different needs depending upon what is the service they are trying to serve. So they might need some preferential treatment for, what the different types of traffic that they are representing, or the different types of users requirement that they are representing. Okay. So for that reason, we might need to do packet classification. Packet classification also helps in flexibility in accounting and billing. Okay. So what does this mean? That, you have like different types of plans for a particular service provider, right? So you have like, there can be some people who pay monthly like 1,000 or 2,000 rupees recharge plans, and some people pay merely 100 rupees or 200 rupees. Okay, so the data pack that they are giving is much lower than the data pack that a person who's giving like 1,000 to 1,000 rupees. That means the speed, that the throughput that they are expecting at the end, that is much higher when the pay is higher rather than the one who's paying a lower amount. Okay, so when you classify packets as such, one, you can give such preferential treatment to different types of packets. Two, that, when you have classified the packets, it is very easy to keep track of like how much of the data has been used by the packet, how much of the resources has been used by the particular packet belonging to a particular users section. So from a user, whatever data packets are incoming, you will get to know, you can keep track of it, and ultimately this will help you, or this will help the ISP to keep track of the user's activities, and ultimately which will help the ISP to do the accounting and billing of the particular user. Not only that, because we are classifying the packets, we will get to know that what is the type of application, what is the requirement from the user's side, and accordingly we can perform actions on those packets so that the customer's expectations can be satisfied by giving the packet some preferential treatment depending upon how much the user is willing to pay, or how much the user is prioritizing its packets. Okay, so with packet classification, we can also manage customer expectations. Okay, and finally, one of the very important tasks that packet classification helps us is for preventing malicious attacks. Okay, so if you can provide preferential treatment for different packets, if you can filter them out, if you can, perform different actions on packets, so you can also look at, as I was talking about, that we can do encryption, we can do authentication, we can drop unauthorized packets. So with all of these facilities that can be provided, we can also prevent, this packet classification will also help in preventing malicious attacks. Okay, so here is the definition that we need to know, that is a collection of rules or policies which define the criteria for classification is called a rule or policy. So we will be using this term rules very often in this chapter. So these are nothing but some policies that are representing some criteria for classification. Okay, so we will see how it works out. So first, let us see the different ways of packet classification. Okay, so let us assume that a classifier of a router consists of some set of rules which can be denoted by like R1, R2, R3 and so on to Rn. Now the rules can be a combination of D values depending upon which field of the header value you are considering. So you consider that a rule is a combination of D values, one for each header field. Okay. Now the rules or each field in a rule can be allowed to have 4 different types of matches, right? So what are those? First is your exact match, that is whatever the value is there in your rule field matches exactly with the header field present in the packet. So that is like some identical match. Okay, so that is known as the exact match. So whatever is there in your header field, you check that. You have that with you and you check the values in the rule field, whichever matches perfectly, that is known as the exact match. And this is generally used in case of specifying the protocols or protocol flag fields. Okay, there you need to have an exact match for the rule field. So this is one way of matching. Another is prefix match. Okay, so prefix match, we do have some idea from the last two classes. So first is that what is the requirement? That is your rule field should be a prefix of the header field. Okay, that means whatever is there in your packet header, your rule field must be a prefix of that. Now you can check that okay, which of these rules match best with the prefix match best as a prefix of the header field that you are currently having. So it is somewhat like our IP address lookup. Okay, we were matching with the help of prefix, right? So it is somewhat like that. So it is generally used for collecting statistics about packets originating from a subnetwork. Now the next one is range match. Okay, so here we will have to see that okay, whatever the header value is in the packet, it should lie in the range that is specified in the rules. Okay, whatever is there in the rule, suppose in the rule it will be specified in the form of a range. Your packet header field value should lie within this range. Okay, so in general, this range match is used to specify, port number ranges. Then we have our regular expression match. So again, your rule must be specified in the form of a string expression, and your header field should match this string expression for a match to occur. Okay, so this is a regular expression match, and it is generally useful for matching URLs. Okay, so this is also generally known as deep packet classification. Okay, so what is basically meant by deep packet classification? That is the in deep packet classification, sometimes the data or the payload part of the packet is also examined. Okay, so what is the website that you are basically looking for? All right, or suppose you want to say that, okay, does this uh, whatever the string you are looking for, whether it matches with the content present in the packet or not. Okay, so these kind of classification, which is dependent upon which basically acts upon the payload part of the packet, is known as deep packet classification. And for doing deep packet classification, we use regular expression match. Okay. Now, few questions on matching. That is, what happens if a packet's header matches with more than one rule? This is a possibility. This can occur. Okay, you can have many rules, and if the contents of a packet's header matches with more than one rule, then you have to take a decision. Now, what are the ways in which you can take a decision? Okay, so one of the easiest ways is to stamp these rules with a cost. That means you associate a cost with each rule, and you try to find out that rule, or you try to select that rule which is having the minimum cost in case of such a scenario where packets header matches with more than one rule. Okay, so this is one. And then again, there is the question that what do you mean by cost? Is it always the monetary cost that we are talking about? It may not be, because cost can represent, how much time will it take. So depending upon the path. Okay, so how much time will it take to reach from a particular source to destination? That can also be represented by, or that can also be represented with the help of a cost. So that means how much a longer path is being taken or how much shorter path is being taken. That can be represented with the help of cost. How much of processing cost is associated for the packet? That can also be a representation of the cost. Okay, so cost is nothing but a measure that will help to break the any tie among multiple matching rules, and this cost can represent different metrics. So for example, it can be the cost of the path, it can be the cost of processing of the packet, it can be the cost of, like, how much time does it take to reach from the source to the destination. That can also be represented with the help of cost. So now let's get to the rules part. Okay, so let us talk about expressing rules. So first is that we can have routers made by different vendors, right? So different vendors can actually have different ways of expressing the rules. But if we have that, then in that case, it will be difficult to, actually, when you have different routers at different points in the backbone network, it will become very difficult to actually have different rules for these different packets and then take actions accordingly. Okay, because you will have integrity challenges. Okay, so most of the times, okay, of course the vendors do have their independence in having different syntax for expressing rules, but most of the times the underlying primitives are more or less same in order to avoid the challenges that will be raised with this integrity challenges. Okay, so this is one point when we are looking for expressing rules. Then when the different vendors have different syntax for expressing rules, then they can also have different fields in a router which can be specified in a different way. Okay, so whenever you are checking or whenever there is a check that is made at the router's end, then it might be different for different routers. Okay, so now we already know that source and destination address fields, they are expressed in terms of prefix notation, and the source and destination port numbers can be either exact specification or they can be specified in terms of range. We just saw in the last matching PPT that we can have 4 different ways of matching. So one of them was range match. So therefore for port numbers we can have either exact match or range match, or it can be a wildcard also. Okay. Now, some of the typical actions that are specified with a rule are that, you can either, this is an example that, you can permit the packet, you can deny the packet, or you can count. Okay, if you want to keep a count, then you can also, the action that can be specified for a rule, it can be also given as count. So this is the way of expressing rules in a classifier. So as you can see here, so these are different numbers, serial numbers of rules. Okay, now you have like some destination address or with the mask here, subnet mask here. Now this is the source address with the mask. Now this is a range match, right? If the destination port is less than 1024, then this is some example protocol that we have kept, that it will, we are not looking at the protocol at all. So it is given as star here, and you deny. The action that you have here is deny. That means you do not allow the packet to go further. Then look at the second rule. So here the destination port should be equal to 80. This is an exact match that is required. Okay, so it's an exact match. Now again, protocol is TCP, so that should also be an exact match, right? So if it is an exact match with the destination port and the corresponding protocol is TCP, then what is the action that you take? You encrypt the packet. Similarly, you can see the rest of the rules that have been specified here. Okay, so these are some ways of expressing rules in a classifier. So you can see that there can be many fields for classification for a single packet belonging to any source or destination, or having a particular destination address. And depending upon all of these different fields, there can be a set of rules, and we can have corresponding actions being taken depending upon these different fields. Okay, so it can be like, what is the port number, what is the source address, what is the port, what is the protocol, what is the type of protocol that is being used, etc. And depending upon that, some actions are being taken here. So remember what we did in the last one, in the lookup algorithms, we were looking for only one field. We were just looking at the destination address, and in the prefixes present at the router, so you were just trying to find the best matching prefix there. Okay, so that was in that case. Whereas in this case, what we are doing, that we have different rules. The rules can have different fields. Now depending upon the type of matching that we want to do, with respect to the values of different fields. It can be an exact match, it can be a range match, it can be a prefix match, or even a string match. That means for deep packet classification, that means a regular expression match. So we can have different types of matching that we can that we want to have, depending upon what is the application that is being supported by the packet, or what is the service that the packet is supporting. So depending upon all of these fields, we take a particular action. Now, of course, whatever we do, at the end of the day, we always look at, what is the corresponding performance metric. Okay, how good or bad the performance is, actually, how good or bad the performance is for the task that we are carrying out. Okay, so in order to compare, or in order to find out that, how the different packet classification algorithms are actually performing, we need different metrics. Okay, so also not only that these metrics also analyze the strengths and deficiencies of each algorithm. And some of the performance metrics are that, first of all, it will be one of the metrics that anyone can think of is that with what speed can we, or how fast can we classify. Okay, so first is the speed of search. This is one type of performance metric, and another is that what is the memory storage that is occupied by the data structures of the algorithm. Okay, these are the two most widely used performance metrics. So let us get to see some of the performance metrics that we are looking here. So first is speed, as I was talking about, that we are actually looking at routers here, and we are looking at how to classify the packets. So at the end of the day, because we are looking for something in the network, speed will always matter. Okay, most of the times, with what speed you are taking care of this particular action or this particular application, so that will always matter. So therefore, speed is going to be a metric. Then as it was told in the last slide itself, that how much of data structures your algorithm is going to take, how much of memory space is being consumed by the algorithm, that is of a lot of importance, that holds a lot of importance. So that is why memory space, that is how much of memory space has been used, is an important metric. Now, with the help of how much of memory space is being used, or how much of memory space will be used, once you get that information, you can think of using faster memory technologies. Okay, so that is one. Then of course, because we are looking for speed here, so faster updates is also an important. That means how fast an update can be made, because there can be changes that can happen in the topology. So we need to make updates as fast as possible. Okay, so so we need faster updates, as it can be seen in the third point here. That is, it is required because the data structures of the algorithm needs to be updated with addition, deletion, and updation of rules. That means for these actions, we might require to do faster updates. Then we have another metric which is known as number of fields. So basically, it will denote that how many, on the basis of how many number of fields the classification is being done. Okay. Then the next one is the implementation flexibility. That means how efficient the algorithm is for the purpose of implementing. Okay. So that is one of the very important fields that we have known so far. Right, so implementation flexibility is also one more performance metric. So now we will get into this part that is known as packet classification algorithms, and we are going to look at different packet classification algorithms here. So packet classification algorithm consists of two different stages. One is that you do a pre-processing, and another is you do a classification. Okay, so let us see what it means. So what is pre-processing? So in general, pre-processing means before you do the exact task, you do some other important tasks on the content. Okay, so the terminology of pre-processing basically means that. But when we are looking at packet classification and we are saying that it is a stage that is before the actual classification, so we have to see that what are the actual actions that are taken when we are talking about a pre-processing stage, right? So first is that what is the purpose of this pre-processing? Okay, so the purpose is that you want to extract representative information from rules and build optimized data structures that capture the dependency among the rules. Okay, so this is the purpose of the pre-processing stage. So basically, you can perform different actions in this stage. It can be used to find the least cost matching rule for every incoming packet. That is one task. Then it is used when new rules are either added or deleted. That is basically if there is an updation that is made. In that case, pre-processing stage can be invoked. And this pre-processing stage is executed in the central CPU of the router. Okay, so this is the purpose and the features of the pre-processing stage. Now we get to the classification stage. So what happens in the classification stage? So this is the place where the exact tasks happen. That means here the actual packets are parsed and the headers are extracted. Okay, and depending upon whatever values are there in the header fields, the corresponding data structure is built during the corresponding data structure that was built during the pre-processing stage, that is traversed to find the best matching rule. So essentially what is happening, depending upon, so look at this slide once again. So depending upon the information from the rules, okay, some optimized data structures are made in the pre-processing stage. Okay, now what happens in the classification stage? In the classification stage, the actual packet is parsed and the contents of its header fields are extracted, and then whatever data structure was made in the pre-processing stage, that is traversed to find the best matching rule. Okay, so these are the two stages, and this is what is the action that is taken in these two stages. All right. So now we are going to look at different ways of this packet classification. Okay, so this is the interesting part that we are coming into. So you have already seen in packet lookup algorithms that we start with a naive algorithm there. So here too we start with a naive algorithm or a naive solution. So what is the naive solution? That you have your different rules present in some data structure, and whatever values are there in your packet field, in your incoming packets header, you try to match it with the rules that are stored, and whichever gives you the exact match, you consider it as the best match. That's what we had studied in the naive solution. So here also we will do the same thing in the naive solution part. So what we are doing, that is we store rules in a linked list in the order of increasing cost. While we are looking at the cost part here, please remember that there can be scenarios where our packets header field might match with more than one rules. Okay, so if that happens, then we need to make a selection. So, or a tie breaking. So that is done with the help of considering the cost. So we choose the one which is having a minimum cost. So that is why we stored the rules in a linked list in the order of increasing cost. Now then the packet's content is compared with each rule. Packet's content in the sense header field content is compared with each rule sequentially until we find a rule that matches the relevant fields of the packet. Okay, so this is this is the basically the steps that I used in the naive solutions part. Now this approach is storage efficient as it requires only O of n memory locations, n being the number of rules that are stored. Now that is okay. So this is efficient because the whatever the number of rules that are there in your there with your router, those we will need only that much of storage for now. But the problem is that the time to classify a packet will keep growing if your n keeps growing. Okay, so with n, the time to classify the packet will grow, and the number of memory accesses will also increase with increase in number of rules. Okay, so this will lead to poor scaling property. All right, so these are the issues that we have with a naive solution. Now one can say that in terms of memory access, number of memory accesses, that by having a cache we can reduce this problem. Yes, we can, but having a cache will also have its own difficulties. So because you know how which data will you bring into the cache, and then after that you need to have some cache eviction policies. So those are also challenges that we need to take care of. Okay, and always please remember always that here we are talking about routers here. Okay, so that means we are basically looking at systems which are mostly they are dependent upon that how efficient your hardware is. Okay, and you are not having a full system with a lot of computation or storage available with you. So these will always be challenges. So therefore, these different types of algorithms that we are talking about, that is lookup algorithms, packet classification and filtering algorithms, they need to be very much efficient in terms of all of these factors, like you know your storage, memory accesses, etc. Okay. Now we'll get to two-dimensional solutions. I hope that I'm making sense because I've talked a lot until now and there have been no questions from your side at all. So after the class, I'll hope that you have some questions for this class. Sorry. Let me get to this one, that is the two-dimensional solutions. Okay. So this is like some enhancement over you know what we had done during our IP lookup. Okay, so in IP lookup, it was a one-dimensional solution, right? You just had some prefixes with you, and you had your packets. You had your destination address with from your packets header, and you just simply tried to match the both of them. Okay, so that was a simple one-dimensional IP lookup problem. Now we are going to look at two-dimensional solutions. Okay, so first solution to this is known as hierarchical tries. Okay, it is almost same as the binary try solution that we had looked at during our lookup class, IP lookup class. Okay, so now remember that here we are not only looking at one field. Okay, we can have more than one fields in order to classify a packet properly and take an appropriate action on it. Okay, so here we are taking only two fields. Okay, so a hierarchical try is a simple extension of the binary try, except that these tries can accommodate two fields. So as you can see here, this is an example classifier with 8 rules. You have rules R1 to R8, and correspondingly you have 2 fields which are represented with the help of some distinct prefixes. F1 and F2 are the fields, and they are represented with the help of some distinct prefixes. Now, depending upon this content that has already been given to you, we need to have a way of efficient classification. So what is the first step that we need to take? Okay, so we had field F1 and field F2 corresponding to different rules as it has been given here. So the first task is that we create a simple binary try with this first field F1. Okay, let us see how it is being considered. So this is our first parent node. Okay, parent node is like, it will always match with all of the prefixes, so it is given as just star. And do we have any such prefix here in this particular table? As we can see, yes, we have. So R8 has field F1 as star. So at this parent node, or we can call it as a root node, so at this root node we have R8 here. Okay. Now F1 is 0 0 star. All right. So 0 0 star, that is R1. Okay. So corresponding to R1, what is the F1 value? That is 0 0 star. So we are drawing the hierarchical try first, depending upon the F1 values that we are having. So the second one, that is R2, the F1 value is 0 star. So you can see 0 star, you are having R2 here. For the third one, that is third rule also, F1 value is 0 star. So similarly, you get R3 here. Now from R4, we have rules in F1 or values in F1 which start with 1. Okay, so therefore it will not go here except for R7, which is again as 0 star. So you put again 0 star, that is R2, R3 and R7. Okay, they are the matches here. Now similarly, when you go to the right child, so again we have to check. Now let us start with 1. So let us start with prefixes which start with 1. So R4 starts with 1 0 star, that is F1 value is 1 0 star. So this is 1, this is 0. So this is R4 here for 1 0 star. R5 and R6 represent 1 1 0 1 1 star. So 1 1 star, R5 and R6. So essentially all of the rules that are mentioned in this particular table have been put here specific to this field F1 only. We have not talked about field F2 as yet. Now remember, we are looking at two-dimensional solutions here, not only one-dimensional. So F1 is this one. With F1 you created this try. Now let's talk about F2. Okay, so what happens for each unique prefix in field F1, we construct a binary try using the corresponding prefixes of field F2. Okay, so this is the task that we need to carry out. So let us look at F2 here. Okay, so first is corresponding to R1. What is the value of F2? That is 0 0 star. So you can see for 0 0 star, this is here 0 0 star for R1. All right, now what is the corresponding F1 value for this particular F2? So that is 0 0 star here. Now next is that you have 0 star for F1. So for 0 star for F1 you have 0 1 star in F2, 0 star in F2, and you have 1 0 star in F2 for 0 star in R7. So here you get 0 star, that is the corresponding under the prefix field of this F1, 0 star. So now under this you will have a small try related to F2 rules, F2 field values. So under 0 star of F1, what are the corresponding F2 values? So first one is R2, that is 0, 1 star. So you can see here 0, 1 star R2. Then again with F1 0 star, what is the corresponding F2 value? That is 0 star for rule R3. So you can see here you have 0 star for rule R3 here. Then okay, you have the zeros here. Then next is the rule R7, which is having the corresponding F2 value as 1 0 star, and you can see here that it has been written here, that is 1 0 star for R7. So similarly you go on for all the other values that are present in the F1 field, and correspondingly you build a try with the corresponding F2 field values. Okay, now what am I supposed to do with the corresponding F2 field values and F1 field values? There has to be some kind of connection between the two now. Only then I will be able to find out that, okay, first let us check the F1 field value, then we will see if it matches the F2 field value also. If it matches all of them, then we say that, okay, then it is a match, or it is the best match. Okay, so we have got the F1 try, now we have got the F2 try. So what we do? Okay, how do we establish the relationship between the F1 try and the F2 try according to the rules in the classifier? So what is the most general solution? That we just simply use a pointer from F1 to F2, and we call it as the next try pointer. Okay, so this pointer is stored in the F1 try, and it points to the node, to the root node for the corresponding F2 tries. Okay, so this entire process, I mean, let me just show you, then I think it will make more sense. Yeah, so this is the corresponding F1 try. Okay, we are not putting the exact F1 try values here. See, look at this. In the F1 try, what you are having? You are having 0 0 star for R1. Okay, so but the corresponding in the F2 try, what was the F2 try here? That is this 0 0 star, that is corresponding to R1 here. So with the help of next try pointer, you just connect this F1 try to the corresponding F2 try. Similarly, for 0 star, you have so many values in the F2 try, right? So what you do, from 0 star, you have a next try pointer, and you point it to the corresponding F2 try. Okay, star is R8, that means R8's F1. I mean, for F1 value as star, this is the corresponding rule, that is R8, and the corresponding F2 value is 1 1 star. So now from star itself also you have the next try pointer pointing to the corresponding F2 try, which represents 1 1 star, that is R8. Okay, so similarly you can do for all other values present in this try. Okay, so this is the way in which the F1 and F2 tries are connected with the help of next try pointer. So let us see some of the features that are relative to related to this hierarchical try. So first is that of the lookup cost. So lookup cost is about O of W square, okay, for the two different fields that we are talking about, and the amount of memory consumed is O of NW. Okay, so we are traversing twice, right? So we require to traverse for many F2 tries for like you have a value for F1 tries, and for each one of them you are looking at the corresponding F2 tries. Okay, so what will happen? The traversals, the number of traversals is actually going to increase with that, right? So if the number of traversals increases, then what will happen? The time for this entire classification exercise that is also going to increase, and the number of memory accesses is also going to increase. Okay, so we need to find out some way so that these large amount of traversals can be avoided. Okay, so this is the features for hierarchical tries. Now next what comes is set pruning tries. Okay, so yes, what we were doing in the hierarchical one, that we had to traverse a lot. Okay, that's what we were looking at. Now set pruning tries is also similar to one of the algorithms that we had studied in the IP lookup algorithms. So you need to tell me that which one we were talking about. Okay, so it is similar to that one of the lookup algorithms. So what we are doing here in case of set pruning tries, that you replicate the rules of the prefixes of F1 and you replicate it in its corresponding F2 try. Okay, so you get a much more exact match in that case. Okay, so how do we construct this particular set pruning try? So you build a try using some unique F1 prefixes in the classifier, and then you try to find out that what can be the possible values that can be added, so that when you are doing an F2 classification, you will have a better match in that case. Okay, so let me just directly go to this diagram itself for better understanding here. So this is same as your hierarchical try was there, but there is a change in this case. Look at this one. So this entire thing now, that is, you have the F1 try and then you have the next pointers being pointing to the F2 tries. This entire concept is known as hierarchical tries. Okay, now when in these hierarchical tries, in order to have some exact match, you are putting all the corresponding matching rules, then you will call it as a set pruning try. So look at this, you have 0 star here now for F1. So you put the next try pointer and you go to the corresponding F2 try, right? So for R1, that is for 0 star, you have only this value, that is R1. For F2, that is 0 star only. So essentially it should give you only this one. If you check your hierarchical try, essentially it was only this left part. But 0 star also matches with 0 star, and it also matches with star. Okay, so all of these corresponding F2 values should also come here. So that is what is happening here. You have 0 star here for R1, as it is given for 0 star in this rule. Now for 0 star, you have 1 star. That means R2. So you have 1 star R2. For R3, you have again 0 star, 0 star and 0 star. So you have 0 star R3. And again, R7 is also 0 star, which is also a matching for 0 star, right? So corresponding F2 value is 10 star. So you get to as 10 star R7. Similarly, again for R8, star will match all of them, right? So the corresponding F2 value for this is 1 star. So star we should also match 0 star. So for 0 star also, you are having the corresponding F2 try value here as 1 star, that is R8. Okay, so essentially you are keeping all of the possible matches that can be there for the corresponding field value. Okay, so this is your set pruning tries. Now the time for the class is over. I'll stop the class here. If you have any questions, you can ask me. Otherwise, the class is over, and I will leave the class after a few moments. Yeah.